Welcome to the session on communication and instruction format. The main components in a typical computer system are the processor, memory, input-output devices, and the communication channels that connect them. The processor is the workhorse of the system. It is the component that executes a program by performing arithmetic and logical operations on data. It is the only component that creates new information by combining or modifying current information. Memory is a passive component that simply stores information until it is requested by another part of the system. During normal operations, it feeds instructions and data to the processor, and at other times, it is the source or destination of data transferred by I/O devices. Input-output devices transfer information without altering it between the external world and one or more internal components. I/O devices can be secondary memories, for example, disks and tapes, or devices used to communicate directly with users such as video displays, keyboards, and mouse. The communication channels that tie the system together can either be simple links that connect two devices or more complex switches that interconnect several components and allow any two of them to communicate at a given point in time. When a switch is configured to allow two devices to exchange information, all other devices that rely on the switch are blocked. That is, they must wait until the switch can be reconfigured. All units in a computer system work in conjunction with each other to formulate a functioning computer system. To have a proper coordination between these units such as processor, memory, and I/O devices, a reliable and robust means of communication is required. Processor to memory communication. The whole process of communication between the processor and the memory can be divided into two steps, namely information transfer from the memory to the processor and writing information in the memory. Communication between memory and processing unit consists of two registers, memory address register MAR and memory data register MDR. The sequence of events takes place when information is transferred from memory to the processor are: the processor places the addresses in MAR through the address bus. The processor issues a read command through the control bus. The memory places retrieved data on the data bus, which is then transferred to the processor. Based on the read time of the memory, a specific number of processor clock intervals are allotted for the completion of this process. During this interval, the processor is forced to wait. Similarly, the following sequence of events takes place when information is written into the memory. The processor places the addresses in MAR through the address bus. The processor transmits the data to be written in memory using the data bus. The processor issues a write command to the memory by the control bus. The data is written in memory at address specified in MAR. The main concern in processor memory communication is the speed mismatch between memory and the processor. Memory access time is generally slower than the CPU's access time. Hence, it is forced to wait for the data. This speed mismatch is eliminated by using a small fast memory as an intermediate buffer between processor and the memory called the cache. Cache memory. Cache memory provides faster data storage and access by storing instances of programs and the data routinely accessed by the processor. Thus, when a processor requests data that already has an instance in the cache memory, it does not need to go to the main memory or the hard disk to fetch the data. Cache memory can be primary or secondary cache memory, with primary cache memory directly integrated into or closest to the processor. In addition to hardware-based cache, cache memory also can be a disk cache, where a reserved portion on a disk stores and provides access to frequently accessed data or applications from the disk. Format of the cache hierarchy. Cache memory is fast and expensive. Traditionally, It is categorized as levels that describe its closeness and accessibility to the microprocessor. L1 cache. L1 cache or primary cache is extremely fast but relatively small and is usually embedded in the processor chip as CPU cache. L2 cache. L2 cache or secondary cache is often more capacious than L1. L2 cache may be embedded on the CPU or it can be on a separate chip or coprocessor and have a high-speed alternative system bus connecting the cache and CPU. That way, it doesn't get slowed by traffic on the main system bus. Level 3 or L3 cache. Level 3 cache is specialized memory developed to improve the performance of L1 and L2. L1 or L2 can be significantly faster than L3, though L3 is usually double the speed of RAM. With multi-core processor, each core can have dedicated L1 and L2 cache, but they can share an L3 cache. If an L3 cache references an instruction, it is usually elevated to a higher level of cache. Cache memory mapping. Caching configurations continue to evolve, but cache memory traditionally works under 3 different configurations such as direct mapped cache, fully associative cache and set associative cache. Direct mapped cache. Direct mapped cache has each block mapped to exactly one cache memory location. Conceptually, direct mapped cache is like rows in a table with 3 columns. The data block or cache line that contains the actual data fetched and stored, a tag with all or part of the address of the data that was fetched, and a flag bit that shows the presence in the row entry of a valid bit of data. Fully associative cache. Fully associative cache mapping is similar to direct mapping in structure, but allows a block to be mapped to any cache location rather than to a pre-specified cache memory location, as is the case with direct mapping. Set associative cache. Set associative cache mapping can be viewed as a compromise between direct mapping and fully associative mapping, in which each block is mapped to a subset of cache locations. It is sometimes called n-way set associative mapping, which provides for a location in main memory to be cached to any of n locations in the L1 cache. Processor to I/O device communication. The method that is used to transfer information between internal storage and external I/O devices is also known as I/O interface. The CPU is interfaced using special communication links by the peripherals connected to any computer system. These communication links are used to resolve the differences between CPU and peripheral. There exist special hardware components between CPU and peripherals to supervise and synchronize all the input and output transfers that are called interface units. The binary information that is received from an external device is usually stored in the memory unit. The information that is transferred from the CPU to the external device is originated from the memory unit. CPU merely processes the information, but the source and target is always the memory unit. Data transfer between CPU and the I/O devices may be done in different modes. Data transfer to and from the peripherals may be done in any of the 3 possible ways: programmed I/O, interrupt initiated I/O and direct memory access or DMA. Programmed I/O. It is due to the result of the I/O instructions that are written in the computer program. Each data item transfer is initially by an instruction in the program. Usually the transfer is from a CPU register and memory. In this case, it requires constant monitoring by the CPU of the peripheral devices. Interrupt initiated I/O. Since in the above case, we saw the CPU is kept busy unnecessarily. This situation can very well be avoided by using an interrupt driven method for data transfer. By using interrupt facility and special commands to inform the interface to issue an interrupt request signal whenever data is available from any device. In the meantime, the CPU can proceed for any other program execution. The interface meanwhile keeps monitoring the device. Whenever it is determined that the device is ready for data transfer, it initiates an interrupt request signal to the computer. Upon detection of an external interrupt signal, the CPU stops momentarily the task that it was already performing, branches to the service program to process the I/O transfer, and then return to the task it was originally performing. Direct memory access. The data transfer between a fast storage media such as magnetic disk and memory unit is limited by the speed of the CPU. Thus, we can allow the peripherals directly communicate with each other using the memory buses, removing the intervention of the CPU. This type of data transfer technique is known as DMA or direct memory access. During DMA, the CPU is idle and it has no control over the memory buses. The DMA controller takes over the buses to manage the transfer directly between the I/O devices and the memory unit. Bus. Inside computers, there are many internal components. In order for these components to communicate with each other, they make use of wires that are known as bus. A bus is a common pathway through which information flows from one computer component to another. This pathway is used for communication purpose and it is established between two or more computer components. Functions of buses in computer data sharing. All types of buses found in a computer transfer data between the computer peripherals connected to it. The buses transfer or send data in either serial or parallel method of data transfer. This allows for the exchange of 1, 2, 4 or even 8 bytes of data at a time. A byte is a group of 8 bits. Buses are classified depending on how many bits they can move at the same time, which means that we have 8-bit, 16-bit, 32-bit or even 64-bit buses. Addressing. A bus has address lines which match those of the processor. This allows data to be sent to or from specific memory locations. Power. A bus supplies power to various peripherals connecting to it. Timing. A bus provides a system clock signal to synchronize the peripherals attached to it with the rest of the system. Instruction format. An instruction format defines the layout of the bits of an instruction in terms of its constituent parts. An instruction format must include an opcode and implicitly or explicitly 0 or more operands. Each explicit operand is referenced using one of the addressing modes that are available for that machine. The format must implicitly or explicitly indicate the addressing mode of each operand. For most instruction sets, more than one instruction format is used. The bits of an instruction are divided into groups called fields. The most common fields found in instruction formats are an operation code field that specifies the operation to be performed, an address field that designates a memory address or a processor register, a mode field that specifies the way the operand or the effective address is determined. Other special fields are sometimes employed under certain circumstances. The operation code field of an instruction is a group of bits that define various processor operations such as add, subtract, complement and shift. Address fields contain either a memory address field or a register address. Mode fields offer a variety of ways in which an operand is chosen. An instruction is of various lengths depending upon the number of addresses it contains. Generally, CPU organization is of 3 types on the basis of number of address fields: single accumulator organization, general register organization and stack organization. In the first organization, operation involves a special register called accumulator. in second on multiple registers are used for the computation purpose. In third organization, the work on stack basis operation due to which it does not contain any address field. It is not necessary that only a single organization is applied. A blend of various organization is mostly what we see generally. Instruction cycle. An instruction cycle, also known as fetch, decode, execute cycle, is the basic operational process of a computer. This process is repeated continuously by the CPU from boot up to shutdown of computer. The circuits used in the CPU during the cycles are program counter or PC. It's an incrementing counter that keeps track of the memory address of which instruction is to be executed next. Memory address register or MAR. The address in main memory that is currently being read or written. Memory buffer register or MBR. A two-way register that holds data fetched from memory and ready for the CPU to process or data waiting to be stored in memory. Current instruction register or CIR. A temporary holding group for the instruction that has just been fetched from the memory. Control unit or CU decodes the program instruction in the CIR, selecting machine resources such as a data source register and a particular arithmetic operation and coordinates activation of these resources. Arithmetic logic unit or ALU performs mathematical and logical operations. Following are the steps that occur during an instruction cycle. Fetch the instruction. The instruction is fetched from memory address that is stored in PC, that is program counter, and stored in the instruction register IR. At the end of the fetch operation, PC is incremented by 1 and it then points to the next instruction to be executed. Second is decode the instruction. The instruction in the IR is executed by the decoder. Third, read the effective address. If the instruction has an indirect address, the effective address is read from the memory. Otherwise, operands are directly read in case of immediate operand instruction. Fourth step is execute the instruction. The control unit passes the information in the form of control signals to the functional unit of CPU. The result generated is stored in main memory or sent to an output device. The cycle is then repeated by fetching the next instruction. Thus, in this way, the instruction cycle is repeated continuously. Instruction set. An instruction set is a group of commands for a CPU in machine language. The term can refer to all possible instructions for a CPU or a subset of instruction to enhance its performance in certain situations. All CPUs have instruction sets that enable commands to the processor directing the CPU to switch the relevant transistors. Some instructions are simple read, write and move commands that direct data to different hardware. The instruction set provides commands to the processor to tell it what it needs to do. The instruction set consists of addressing modes, instructions, native data types, registers, memory architecture, interrupt and exception handling, and external I/O. An example of an instruction set is x86 instruction set, which is common to find on computers today. Different computer processors can use almost the same instruction set while still having very different internal design. Both the Intel Pentium and AMD Athlon processors use nearly the same x86 instruction set. The instruction set can be built into the hardware of the processor or it can be emulated in software using an interpreter. The hardware design is more efficient and faster for running programs than the emulated software version. Example of instruction set are add, to add two numbers together, compare, compare numbers, input information from a device, example keyboard, jump, jump to designated RAM address, jump if, conditional statement that jumps to a designated RAM address, load, load information from RAM to the CPU, out, output information to the device, Example, monitor. Store information to RAM. In the early days of computing, the cost of computer memory was very high and the amount of memory available tended to be limited by this factor. Limiting the size of a program in memory was therefore an important consideration. Program size was influenced by the number and size of the instructions required to carry out a particular task. An instruction set with a high code density used powerful instructions that could perform several functions at once. There are two prevalent instruction set architectures. Complex instruction set architecture (CISC). The CISC approach attempts to minimize the number of instructions per program, sacrificing the number of cycles per instruction. The other is reduced instruction set architecture (RISC). RISC does the opposite, reducing the cycles per instruction at the cost of the number of instructions per program. CISC architecture. Computers based on the CISC architecture are designed to decrease the memory cost. Because the large programs need more storage, thus increasing the memory cost and large memory becomes more expensive. To solve these problems, the number of instructions per program can be reduced by embedding the number of operations in a single instruction, thereby making the instructions more complex. Example of CISC processors are IBM 370-168. It was introduced in the year 1970. CISC design is a 32-bit processor and 4 64-bit floating point registers. VAX 11780. CISC design is a 32-bit processor and it supports many number of addressing modes and machine instructions, which is from Digital Equipment Corporation. Intel 80486. It was launched in the year 1989 and is a CISC processor which has instructions varying length from 1 to 11 and it will have a 235 instructions. RISC architecture. Reduced instruction set computer is a type of microprocessor architecture that utilizes a small, highly optimized set of instructions rather than a more specialized set of instructions often found in other types of architectures. It is a dramatic departure from historical architectures. Most RISC architectures have fixed length instructions, commonly 32 bits, and a simple encoding which simplifies fetch, decode and issue logic considerably. RISC designs have a model where the instruction stream and the data stream are conceptually separated. This means that modifying the memory where code is held might not have any effect on the instructions executed by the processor because the CPU has a separate instruction and data cache, at least until a special synchronization instruction is issued. On the other hand, this allows both caches to be accessed simultaneously, which can often improve performance. Examples of RISC processors. The ARM architecture dominates the market for low power and low cost embedded systems. It is used in a number of systems such as most Android based systems, the Apple iPhone and iPad, Microsoft Windows phones, etc. IBM's power architecture. It is found in the GameCube, PlayStation 3, Xbox 360 and other gaming consoles. The MIPS line, used now in the PlayStation, PlayStation 2 and residential gateways like Linksys WRT54G series. Now let us summarize the session. The most important and expensive component of a computer is the processor. All the other characteristics of computer depend on the maximum utilization of the processor. The processor should get the data and instructions as and when required. The communication and instruction formats play a key role in this. Hence, in this session, we have seen the communication between processor and memory, that between processor and devices, etc. The different types of instruction formats and the two important architectures such as CISC and RISC are also mentioned here. Hope you enjoy this session. See you next time. Until then, bye.